lesson in Edmentum. So we're just doing half of that today. I want to start with a review of what we started with. Oh, there's Braden again. I want to start with a review of yesterday's. So we started graphing. We started looking at like the important parts of a parabola and a quadratic. But we haven't straight up graphed it from scratch yet. So that's what we're going to do today. And I want to do it in both forms so that we're ready and exposed to both ways of doing it, whether it's in vertex form or in standard form. Morning, Braden. Can you hear me okay?
Yeah, I can hear you.
Awesome. All right, thanks for joining. All right, everybody. So my goal is to have this lesson end sooner than normal, not like a whole hour. And that way we can start work on our homework problems together. So that's my goal for today. Hopefully I can make this happen. It's been several weeks and I still haven't had shorter lessons yet, have I? So thank you all for working hard and being patient. Here we go. So I want to start with a couple problems from yesterday. Yesterday I did assign everyone to do the mastery test. So these are 5 problems that you could have gotten in your mastery test. So I want to do these with you. So don't worry about taking notes on these next 5 slides because we're just going to kind of do problems from yesterday's mastery test together. Then we'll start notes when we start our new stuff for today, our graphing. Okay, I thought this was an interesting question.
So you don't do notes right now?
Yeah, you don't have to do notes right now. We're going to do 5 questions from yesterday's mastery test. And it'll take too long, I think, for everyone to write all this down. If you want to take pictures, that's all good. But I don't want you to spend your time, trying to write all this stuff down you're going to see. So this one I thought was actually a good question to start with because it's like testing how much we, I guess, understand about the idea of our parabolas. Remember, quadratic function, that just means our polynomials that we've been factoring in unit 2. So things of this nature right here. Quadratic functions, and remember from yesterday, when we graph these quadratics, they look like this. They're like bowl-shaped. They can face up or down. And actually, I'm kind of exaggerating the shape here. They do come to a nice finer point than this, don't they? So we saw them yesterday graphed, and they're more like that, with like a single point at the very top. So anyways, that's just the general picture of them. So look through this list of 5 statements below with me. And we need to pick any of them that are true about the x-intercepts of quadratic functions. So look through the list and tell me if you notice any that you can eliminate, meaning it's not true for sure, or if there's one that you think is true. So take a minute and tell me if you feel comfortable speaking to any of these, please.
Can't you eliminate that an x-intercept is located at the point of the function where the value of x is 0?
An x-intercept is located at the point on the function where the value of x is 0. Yes, we can eliminate that. Let me draw a picture here to kind of demonstrate what's going on. Where the value of x is 0. So let's say we had a quadratic graph. X is 0. Remember the x, hang on. The x-axis is our horizontal one, of course. So on that x horizontal ruler, it's 0 right in the middle, right? They both are. Y and x are both 0 right here. So this third statement, and I think that was Manaya, right, who pointed this out? Forgive me if I'm wrong. Was that Manaya?
Yes.
Awesome.
Yes.
Thanks, Manaya. So what she pointed out is this third statement is incorrect all the time, An x-intercept is located at the point on the function where the value of x is 0. This statement is saying that it has to be right here all the time, that's the x-intercept. That's not true. When the x is 0, this is a point where x is 0, this is a point where x is 0, this is a point where x is 0. Everything on this line, the y-axis, is when x is 0. So the statement 3 is out. We can eliminate it because it's not true for sure that all x-intercepts have to be on this line. This one right here that I'm putting a dash around now, that's the only one that could ever be the x-intercept when x is 0. What we could say to fix statement 3 is when the value of y is 0. Now that's true. When y is 0, that's the x-intercept line. So this spot, this spot, this spot, these are the examples we saw yesterday of x-intercepts. When y is 0, all these are okay. So we can say this one's false. We would not click it because it's not always true, like Mania noticed. Okay, now I'll give you guys a hint. There are 2 in this list that are true. Does anyone think they see a true one, or have you eliminated any others that are not always true, or they may be false all the time? Any other ideas? I'm going to delete this work I did for the last one. Okay, let's look at the rest together. I'll try to go through these quick. Let's look at I'm going to label these 1, 2, 3, 4, and 5. Let's look at number 1. If x is equal to a is an x-intercept of a quadratic function, then x plus a is a factor of the function. Okay, so yesterday we looked at where the x intercepts, and also known as the zeros, remember, x-intercepts, same thing as zeros. We're going to refer to them both ways. Maybe I should actually spell that with an E, zeros. At any rate, zeros. We looked at solving for the zeros just with the equation, just with the math, and then also finding them on the picture when it's graphed. We want to be able to find them both ways. So they're saying if x is equal to a, so a is some number, let's see what that looks like in a hypothetical. So here's our hypothetical parabola graphed out, quadratic graphed out. Here is one of the x-intercepts in our hypothetical. Let's call that a. Okay, this is like a units away. Maybe it's 4, maybe it's 20, maybe it's 112, whatever. The point is we're going to call it a. So x is equal to a is an intercept. So that means for when we factor it, it should be the opposite sign in the factor, x minus a. All right, sorry, technical difficulties. Keep and start over. Anyways, sorry about that. So when we factor it and we get x plus a number, x minus a number, just like we were doing in Unit 2, these values are the zeros, but it's always the opposite of the sign it looks like. So for this, if x minus a was our factor, then that means x equal to a, that a number is the actual 0. And just to throw on an extra example here, maybe the next one is x plus b for the next factor. So that means what value of b would I plug in for x there to make this whole parentheses a 0? It'd have to be negative b. So x is positive a, x is negative b. Those would be our factors in that hypothetical. So number 1 is false also, because x plus a wouldn't work. It would need to be x minus a. If x is equal to a is an x-intercept or 0, then x minus a is a factor. Okay, we'll look at one or two more that deal with this because I think that's a good topic and we probably need more practice with it. Number 2, an x-intercept of the quadratic function is also called the 0 of the function. Any thoughts on number 2? An x-intercept of a quadratic function is also called a 0. Can anyone speak to that for me? Is that true?
Yeah.
Aaron, high five. Thank you. Yes, that's true for sure. We found a true one finally. This is just a straight up definition. X-intercepts are also called zeros. And I mentioned that earlier for number 1. Thank you, Aaron. Okay, number 4, a quadratic function can have up to 2 x-intercepts. Or zeros. A quadratic function can have up to 2 x-intercepts. That means it could have 0. It could have like no x-intercepts. It could have 1 x-intercept, or it could have 2. But it couldn't have any more than that. Couldn't have 3 or more. Any thoughts on this statement, number 4?
I think it's true.
It's true. Yes. Thank you. Was that Leja?
Yeah.
Thank you, Leja. True. Yeah. So we saw one example yesterday that looked like this. I know it's getting kind of messy. Let me show you at the very top here. We saw one example, I think, where we had a parabola without any x-intercepts. If we had one up here, here's an example of 0 x-intercepts, right? No x-intercepts. It's never crossing the x-line. So that can happen, but most of the time, it'll be down below somewhere maybe, and it crosses over, like lots of our other examples that have zeros. And then we haven't looked at a case yet where it's just a single x-intercept. We'll look more at those later. Let me show you what that looks like. Sorry about the mess. On the right side, I've got a new graph. And if I had a quadratic that landed right on the line like this, that's a case of 1 x-intercept, a single. We'll look more at that later. Anyways, that's a case of what that looks like. We can have no x-intercepts, we can have 1 or 2, and that's it. So that means our last one has to be false. All quadratic functions have exactly 1 x-intercept. Not true. False. Because we know that they can have 2, and most of them will have 2 x-intercepts. Or they could have 0. Okay. Let's look at a couple more questions. Remember, these are from the mastery test that I issued to everyone as homework yesterday. So you may come across these exact problems, or you might have ones that are like it, but different. So if for those of you who have done it already or attempted it, thank you for doing the homework yesterday or trying it at least. And if you haven't yet, I want you to do it today. Try doing the mastery test today. Okay, which expressions are factors of the quadratic function represented by this graph? I hope that's large enough for you all to see. How do we find the factors using the graphed picture, the function graphed? Any thoughts? Any ideas? Remember, what do they mean by factors? Factors means we started with a polynomial that looks like this. Then we did our factoring process, and it looks like this at the end. X plus something, X plus something else. Maybe it's minus something. But the point is we've factored it, and we have it in these two parentheses now. No more X squared. See? These are how we find the zeros. Find the zeros, remember? And if we have our picture, we can actually see the actual real zeros. So let's look at our blue line on the right. That's like the only evidence they gave us for this question, right? The only thing we have to work with. I see a zero right here. It's crossing the X line. Remember, X-intercept is a zero. And the next one is crossing right here. So now our question is, well, what numbers is it crossing at? So for the first one, that first x-intercept is at 0 on the ruler. So as a point, it's 0, 0. If I wanted to write it out as the x-intercept, x is equal to 0. Then for the other one, it's at positive 6. So x is equal to 6. So if my two zeros, or if my two x-intercepts are 0 and 6, we're going to change the sign on those and put them into our parentheses. So here we go. Y is equal to x minus 6, and then x plus 0. We could, now 0 is kind of a special case. We could write minus or plus. Doesn't really matter because x plus 0 or x minus 0 is just equal to this, folks, x minus 6 times x. So this would be our factored form of our parabola or quadratic. And we know that just based on the picture. So there's our factors. X minus 6 and plain x. So it looks like this is the option that matches that. So if we're given a picture, a graph of a parabola already made, we can find the zeros just by examining it. Positive 6 and then 0 for this one. And then we can show the factors by switching the signs on those. So if it's positive 6, our factor is x minus 6. Because we're asking what makes this whole thing, this whole parentheses, equal 0. Well, x would have to be positive 6. That's what we know from our picture. So then we kind of flip it and make it backwards for our factor. Any questions so far? Comments, please. All right. If there are no questions, I do have someone's mic on, so I'm going to mute you. So sorry about that. If you have a question, feel free to turn it back on and let me know. Please do. All right, no questions. Let's look at another one. Oh, here's a good one. Straight to the point and test this on our zeros and factors. The zeros of a function f, that means like f of x is equal to this. We don't know a, b, and c. The zeros of function f are -1 and -5. Which equation could represent function f? So if the zeros are -1, -5, then which one of these below would be our factors? Anyone want to take a guess or a stab at this one, please?
Wouldn't it be the x plus 1 and the x plus 5?
Beautiful. Yes, thank you, Aaron. Yeah. Can you tell me in your own thoughts, in your own words, how you knew it was that option, please?
Because I remember you saying something about like you flip it. So it would be, instead of negative, it would be positive.
Absolutely. Absolutely. That's the fast, easy way to think about it. That's how I think about it, and I want you guys to understand you can use that too as a shortcut. If we know the zeros are these numbers, change the sign, flip it, and it'll be x plus, those numbers. All right. Any questions, concerns on this? Okay. Okay, I want to really quick show you one more here, and then I think we need to get on with some new stuff of how to graph these from scratch. So this was a confusing looking question. It's a word problem, and we have to use a graph in some tools. So maybe I should have opened this up in the actual test. If you run into one like this, read through your problem, try to make sense of what they're telling you in the word problem. They notice that they did give you a straight up equation to use, and this is in vertex form. So remember, in vertex form, it'll be x plus or minus a number. In the original form, we say it's x minus h squared, and then plus k. H and k are the vertex. So Jason kept track of the number of songs he downloaded each week for 10 weeks, 10 consecutive weeks. This function models the number of songs he downloaded, where x is the number of weeks. Okay, so here's our function. If we plug in numbers for x, like 1, 2, 3, 4, and simplify, it's telling us how many songs this person has downloaded. What do they want us to do here? Plot the axis of symmetry and the vertex. So really, they're not asking us to do too much. We just have to make a line for the axis of symmetry and the vertex itself. The vertex should be pretty easy to find. They're giving us the equation here, x minus 4 and then plus 60. So if we compare that to our generic version of vertex form on the right, whatever minus is, whatever's being subtracted in the parentheses is h. So our h is 4. And our k value is 60. Okay, so that means our vertex is at 4, 60. So on our graph, we need to find that location. To use the tool, you're going to click on point. And then after that, if you just click on any spot in the graph, it'll make the point where you want it. If you make a mistake, don't worry about it. Just hit the undo button or the reset button on the top right, and it'll let you redo it. So play around with these ones that have tools for you to use until you feel better using the tools. And you can always reset it. And if you need to, we can always do it together during our office hour or at another meeting. If you want to tell me, we can do it together. Okay, so there's our vertex. And then line, we need to make our axis of symmetry. So to use the second tool, the line, you're supposed to click on anywhere on your line. So I would click here on the vertex we just made. And then you have to hold down and pull in the direction you want your line. And when you release, then it'll make your line go all the way. Now remember, axis of symmetry cuts the parabola in half and it goes through the vertex. So in this question, they're not asking us to make the whole parabola. They're just asking us to find those two locations or those two items, the vertex and then the axis of symmetry. Okay, now let's start graphing. I'm going to skip this one. How to graph a quadratic. I want to show you in both forms how we can do this. So go ahead and copy this down. We're going to do it in vertex form on the left and then standard form on the right. And believe it or not, these are the same quadratic. Okay, I just have them in both forms. If you want to see how the vertex form on the left equals the standard form on the right, we multiply out x minus 3 squared. I'll show it to you really quick here, just in case, so you see how they equal each other. So we multiply out those. So remember, think back to the beginning of unit, I think it was the beginning of unit 2, multiplying. So x times x negative 3 times x, then again negative 3 times x, and then finally negative 3 times negative 3. And there it is. X squared minus 6x plus 10 equals the one on the right. Okay, so I wanted to show you with just one, one figure, one function, but both forms. So starting with vertex form here, we have y equals x minus 3 squared, the whole parentheses, plus 1. So we just talked about this. The vertex is whatever's being subtracted, and then the whatever's on the outside, hk. So our vertex here is 3, comma 1. So step 1 is just identify the vertex. 3 comma 1. So I don't know this actual shape yet of this parabola, but I'm going to make my y-axis. I'm going to make my x-axis. And I know that the vertex lives at 3, 1. So let's put that spot on our graph somewhere. So I'm going to go 3 units to the right, and then at least 1 unit high. There's my vertex. Okay, now we just talked about axis of symmetry. So without knowing if this without knowing what this total parabola looks like, we do know where the vertex is, and we also know that right through this is our axis of symmetry, meaning this is where it's being cut in half and made into that mirror image. So here's what we're going to do next. Back on the left side with our actual equation in our math, we're going to do a couple points. We're going to put a couple x values into the function and solve for y. And how do we know which x values to use? We're going to pick a couple x values that are in the neighborhood of 3, whatever h is, because we know we want to find the points that are around it. So like, for instance, let's make a table here. So we already know one point on our line is 3, 1. So I'm going to put that in my table. Now to do some points in the neighborhood of 3, let's go 1 behind it and 1 in the front, meaning 1 lower than 3 and 1 past it on the other side, 1 bigger than 3. So we'll plug in 2 and we'll plug in 4 and see how high those points are for outputs when we plug in 2 and 4 for inputs. And then also I want to take another step back and another step forward from 3. So 1 more unit on the other side would be 1, and then 1 more unit on the other side of that would be 5. So I'm kind of waiting to make my table until I know where's the vertex, where's the axis of symmetry, and that'll tell me what's in the neighborhood, what's in the general vicinity of h. H is 3 this time. Now, another thing to keep in mind is that we have symmetry, right? So if we plug in 2 of these, if we do the 4 and the 5, then we don't have to do the 2 and the 1 actually, but I still want to put them on my table just to keep track of them. We don't have to do them because they're going to match the heights of the 4 and the 5. So let's do this now. I'm going to take my function, just rip it right from the top and write it down somewhere to start. And now I'm going to plug in, let's do the smaller numbers. Let's do 2 and we'll do 1. Okay, so let's plug in 2 for x right now. Y is equal to 2 minus 3 squared plus 1. I'm choosing to do the smaller numbers, not the larger numbers of 4 and 5, because generally speaking, smaller numbers are easier to work with in math. So if we have a choice, let's pick the smallers. Okay, 2 minus 3 is negative 1. So negative 1 squared gives me a 1. Negative 1 times negative 1 is positive 1. 1 plus 1 is 2. Okay, we plugged in a 2 for x and we get out 2 for y. Awesome. So let's graph that one. Put some more spaces on my graph here. Get it ready. Remember, when you're making your dashes for numbers, try your best to make them the same space apart. And it's okay if it's not perfect. Mine's not either. So the point we just found was 2 comma 2. So that's 2 to the right and then 2 high right here. Now remember, we have symmetry around our line in the middle, so the axis of symmetry. So we can actually put 1 right across from this on the other side right here. So 4 comma 2 is also on our graph. And there's the beginning of our parabola. And now let's do a 1. We're going to plug in 1 for x. So back to our table on the left, we got to find another point here. So I'll plug in 1 for x. So I'm doing it at the bottom for space. Y is equal to 1 minus 3 squared plus 1. Notice that the function's the same, but x is being swapped out with the value of 1 now. 1 minus 3 is negative 2. Negative 2 squared will give us a 4. Negative times negative makes it positive. 4 plus 1 is 5. So our output is 5, 1 comma 5. So 1 to back on the graph now, 1 and all the way up to 5. So that's where that should connect to. And after that, let's just kind of estimate what the rest looks like. Now for 5, it's also going to be as high as the 1. Remember, because of the symmetry. So let's put that point in as well. And we've graphed in vertex form. So how to start this whole business is to find the vertex. That tells us basically where the middle of our picture is, the middle of our graph. And then in this case, it was 3. X is equal to 3 because of the h value. So whatever's in the parentheses x minus number, that is kind of the middle of our picture. Pick a few spots to the left of it and to the right of it. And then we have to at least do 2 of those. I did plugging in 2 and then plugging in 1. And we can use the symmetry to figure out what the 4 and the 5 look like. They're going to match exactly every time with our parabolas. Any questions, concerns? All right, do we need more time on this before we start standard form?
I need a little bit more time to copy down, Josiah.
Thanks for telling me, Leisha. Okay, I'm going to wait a minute, and then you guys just finish copying, and let me know if you need anything else.
Thank you.
Thank you for telling me.
Okay, I think I'm done copying, Josiah.
For sure. Thanks, Leisha. And we just passed the minute mark. And is there anyone else who'd like me to wait before we start graphing in standard form? Pardon me. Okay. Now I'm gonna delete what I've got on here. Okay, so I'm running out of space. Now, what we're gonna do for standard form, remember, it's gonna be the same picture that we just made. Okay, we should get the same thing. We should have a vertex at 3, 1. And then it'll face up like we saw last time. But when we're in standard form here with A, B, and C, instead of like what we see on the left, we don't have the vertex just given to us, right? That's a problem. That's frustrating. How do I know where to start? Here's a little formula we're going to use. So this is super important. Make sure to copy this down. We use this formula to find the axis of symmetry. Use this formula for axis of symmetry. Here it is. X is equal to negative b over 2 times a. We don't care about c. We don't need c. We need to know, though, what is b, what is a. And this little mini formula will tell us every time where to start our parabola. So let's do that. Our b in this problem is negative 6. Okay, the sign matters. So bring the sign with it. I'm going to plug that in here. So negative b becomes negative 6. Okay, we've got a double negative going on with this example. The formula is already negative b, and then if you bring in a negative number, it becomes double negative. Then 2 times a. So a in our problem is 1 because there's no coefficient there in our polynomial above, right, for the x squared. So it's just 2 times 1. Simplify this business. So negative 6 becomes 6. 2 times 1 is 2. 6 divided by 2 is positive 3. So that means x is equal to 3. What that just told us is the axis of symmetry. So back to our graph. I'm just kind of focused on the x line for now. So pretend we didn't do the last graph, right? We're graphing, but we're doing it in standard form now. So if I didn't know what the last one looked like, I would start my graph. I just found x is equal to 3 using my axis. Here, let me circle this. It's the axis of symmetry formula. X is equal to negative b over 2a. Okay, so what it told me is that somewhere along this line, x is equal to positive 3. I'm just going to make it dashed. Somewhere along this line is my vertex, but it doesn't tell me where the y is for, or I guess I should say the k, right? We want to know where does the vertex go on that axis of symmetry. All we know right now is it's somewhere on x is 3. So to find the height of it, to find the k value, basically, the vertex, we have to take x is 3, and we're going to plug that back in to the original equation. So let me do that over here on the left, okay? So now we're finding where is k. We're finding where does the vertex live. So here's the equation. And we're going to plug in 3 because we know along that line of x is 3 is the vertex. So here we go. I've switched out x's for 3's. Now we've got to do some simplifying. So 3 squared, 3 times 3, 9. Minus 6 times 3. So 6 times 3 is 18. And then we've got our plus 10 at the end. 9 minus 18 is negative 9. Negative 9 plus 10 is positive 1. So that means at 3, comma 1, because remember, we just had an input of 3. So if I make a table, I'll put that over here. We put in 3, we got out 1. So generically, we just found like any random point on our parabola. But we know it's not just a random point, it's actually the vertex. We know it's the vertex because it's on the line of symmetry. So there's 3 comma 1. There's our vertex. Now we kind of revert to what we did earlier. We have to find a couple points in the neighborhood. So we can plug in 1 and 2, just like we did before. And then those are going to correspond to what we get for 4 and 5, because it's going to be a mirror image. So we've already done this for the last problem, but then what we would do next is plug in 2. 2 is in the neighborhood of 3. Or if you chose to, you could plug in 4. You're going to get the same answer. They're right across from each other, remember. So let's plug in 2 real quick. And we're using our standard form so you can see what this looks like. So I'll do this in the white space in the center bottom here. So we've got y is equal to our original, plugging in 2 this time. 2 squared gives me 4 minus 12 plus 10. Okay, 4 minus 12, negative 8. Negative 8 plus 10 is 2. So my input was 2, and my output was also 2. That means I can go 2 to the right and 2 high for this spot on my graph. And then the other location on the other side is going to be the same height right here. So there's the beginning of our parabola. And then, of course, if we plug in 1, we're going to get, what did we get last time? It was up to 5. So 1, 2, 3. So we know by plugging in 1, I'm not going to do that now. We would get a 5. And then over at 5 comma 5 is the other side. And it kind of goes on forever in that way. So when we're doing it in standard form, we have to basically start with this special formula I gave you on the right. X is equal to negative b over 2a. That's where the line of symmetry will be. And then we have to plug that number into the standard form equation for x. And that tells you exactly where the vertex is, how high it is. And then we can go to town and find some other values on the parabola line in the neighborhood of 3, the line of symmetry. Okay, I'm going to wait another minute just in case people are still copying. And then I want to look at least one more example with you. And then I made homework to be just doing it on paper, practicing doing some graphing using these skills. So we're not going to do a mastery test today. It's going to be some parabolas to try graphing yourself on paper. I'm just going to wait a few moments to let you finish writing down. All right, let's do another new example. Okay. Graph the quadratic. Y is equal to x minus 5 squared minus 2. Is this in vertex form or in standard form? When it looks like this, oh, go ahead.
Oh, I'm sorry. I thought you were asking. Go ahead, just say.
No. I would rather hear from you guys, please.
It's in vertex form?
Very good. Very good. I'm glad you recognized that. H is whatever's being subtracted here. So H is 5. It's not negative 5. It's the number being minused. So think about the H is always the opposite of what it looks like. I know that's tricky. K is taken at face value. It's negative 2. H is always the opposite, kind of like our zeros are, right? K is taken at face value. So our vertex here is 5, negative 2. So this is our starting point. We know exactly where the vertex is. This is wonderful when they're in vertex form already. It helps save some steps for our graphing. So it tells me exactly where what my graph needs to look like because I know that's where it starts. So that means 5 to the right and down 2. So I'm going to make my totally straight, non-crooked lines here. Okay, so there's my x and my y. And I know that I need to go 5 to the right, positive 5. I try my best to make those spaces in equal distance apart, right? If they're all super small and then super big next to each other, it's going to look warped. So try your best to make them look even, right? Um, but also keeping in mind, it's okay if it's not perfect. So it's just a balance. We're trying our best to make it look good, but don't be hard on yourself when mistakes happen. So, and mine are not going to look perfect either. It's all good. We're all human here. 1, 2, 3, 4, 5. And I guess we'll label the rest of these just so we know what's up. And then it's got to go down 2, low 2. So on the y, here's -1 and -2. Let's put a couple more in there. -3, -4, at least those. So now we graph the actual vertex, 5, -2, right here. Cool. So that tells me where the vertex is and the axis of symmetry. So I know this parabola is going to be mirrored along this line. Okay, so now what we do is we're going to plug in some numbers into the equation, the function, in the neighborhood of 5. So we can do plugging in 3 and 4 or 6 and 7. And you know what I just realized is even though it is usually better to plug in lower numbers because smaller is usually easier to work with, we're going to keep getting negatives in our parentheses. So if you look above at the equation, it's x minus 5, right? So if I plug in 4, that's going to be -1. And if I plug in 3, it's going to be -2. So if you'd rather work with positive numbers, then I guess plugging in the 6 and the 7 would be better. So let's try that this time. So I'm doing my work on the right here. So y is equal to x minus 5 squared minus 2. I'm going to plug in 6 this time. Remember, you have a choice. You can plug in anything you want, but pick 2 numbers in the neighborhood of 5, wherever that line of symmetry is. So I'm going to do 6. So 6 minus 5 squared minus 2. 6 minus 5 is just a 1. Yay! That's easy. 1 squared is just 1. 1 minus 2 is finally -1. And I didn't write down my y equal, so I'll put those in. So y is equal to -1. So if we make a table to keep track of this information, and I'll do mine over on the left side here, try to make it out of the way. We already know the vertex is 5, -2. We just plugged in 6, and we got out a -1. Let's plug in 7. 5, 6, 7. But I'm out of space. So let's see, I'll do this on the right side. Starting from the beginning. Plug in 7 this time. 7 minus 5 is 2. 2 squared minus 2. So 2 times itself is 4. 4 minus 2 is 2. We plugged in a 7. We got out a positive 2. Okay, and I didn't actually graph the last point, did I? So we have to put our points, our coordinates, onto the picture now, which I missed. Let's do 6 comma -1. So that's over to the right 6 and down 1. And then we've got 7 comma 2, positive 2. Notice that. So I better put that on my picture here, going upwards to the positives. 7 over 7 and up 2, right there. So here's like half of my parabola. Now remember, we know the general shape of these, so don't draw them as like rigid straight lines. We know that these are supposed to be curved, so just do your best to make it look curvy. Look, mine's not perfect, but at least it doesn't look like a straight line, right? So just aim for that. Now, what about the other side? I'm going to put on my table, just to keep track of what's going on, a 4 and 3, the other numbers going backwards on the list. And we can make a mirror image with what we got for 6 and 7. So 4 will go to -1, and 3 will go to 2. Whatever we find for one side of the parabola will match the other side. So 4, -1, and 3, comma, +2, just like our 7 went up to +2. And now I try to connect those with a nice curve. It's okay, pretty good. But I see the vertex, I see the line of symmetry, and I see the shape of this parabola. And darn it, I failed my goal of trying to finish early, of course. Since we've got 5 minutes, I'm going to just do one more example. I wanted to do one more example in standard form so that you get a chance to see that again. So here we go. Example 2, graph the quadratic, and this time it's in standard form. Uh-oh, they don't tell us the vertex right away. That sucks, but we can still work with this. Identify the A, B, and C's. A is 1, B is 8, and we don't actually need C, do we? But we need A and B. Remember, our formula we use for axis of symmetry, x is equal to -b over 2 times A. So plug in the B, plug in the A. So -8 over 2 times 1. All right, -8 over 2, and that becomes -4. So x is equal to -4. This is where the axis of symmetry lives. So let's start our picture over here on the left. -4 this time. 1, 2, 3, 4. So somewhere along this vertical space is where my vertex lives. To find where, we've got to plug -4 into the equation. So let's do that. So starting from the beginning, we're plugging in -4. Pay attention to those signs. If you've got negative numbers and you're plugging it in, so -4 squared, -4 times -4, that'll give us a positive for sure. Negative times negative. 4 times 4 gives us 16. The middle term will be negative. 8 times -4. So that's -32. Okay, now just go down the line and add or subtract these together. So 16 minus 32 is actually -16. And then -16 plus 10 will give us -6. So we got y is -6. So that goes with what we plugged in the beginning, -4. So -4 down 6. Okay. 1, 2, 3, 4, 5, 6. So there's our vertex. -4, -6. So now we're at the point where we can just start doing what we always want to do, is plug in numbers around the neighborhood of -4. So we're going to plug in like -3 and -2 and match those up with -5 and -6. So why is it, I'm not going to have time to do all this probably. Starting from the beginning, let's plug in -3. Okay, -3 squared gives us +9 minus 24 plus 10. 9 minus 24. That's tricky. I'm going to do that on my calculator. 9 minus 24. Negative 15. Plus 10. Negative 5. So we plugged in negative 3, and then it goes to negative 5. Cool. That'll mirror on the other side. So negative 5, negative 5. There's the beginning of our parabola. Do one more so you see how high it's going to the next step. And it looks like it's time to go. So forgive me for rushing this. Honestly, I thought this would have been faster. Please take a picture of these three and try doing these today. I think you have enough tools.